So please give Lesley a big round of applause.
All right, great, it's working. Everyone can hear me all right? Perfect, all right. So hello everyone, welcome to my talk on effective observability patterns in microservice architectures. So just a little bit of background on me. Prior to beginning at the New York Times, I spent all of my career in ed tech. So I've seen ed tech change and grow many times, but I think I can speak for everyone in ed tech when I say that no one ever expected the challenges we have to face when the world decided to go remote. Right? Challenges I never thought I'd see in my career happen during remote learning times, going from 40 million users to over 120 million users in the course of 5-6 weeks. Migrating school districts for entire countries like Mexico onto Google Workspace and Classroom, and all the production issues that had to happen, that had to be solved to support all of that, right? And so none of us were fully prepared, if I'm being honest. And so as you might imagine, this gave me a very deep appreciation for the perils of debugging production. And so I've taken this experience with me as I continue to focus on reliability management and observability as a tech lead and engineer. And so this talk is a compilation of learnings from my past and current experiences building developer platforms and focusing on reliability management. And so now I like to start my talks off by providing a shared definition of the topic I'm going to be presenting on. So we'll begin there. And so as much as I hate repeating words on a slide, I'm going to do it if only for emphasis. And so borrowing Liz Fong-Jones' definition of observability, observability is the ability to understand what's happening inside of your software systems to debug problems you've never had before, just using telemetry emitted by your applications. More importantly, she says, it's not just about a specific tool, it's about a team's ability to analyze that telemetry data. And so this is a loaded definition, but there are some components here that are important to highlight. The first is this first part about being able to understand the internals of your software systems, just using telemetry, which is data that represents the inputs and outputs of your software. You most commonly know these to be traces, logs, and metrics. And the reason for this is because the hardest and most interesting problems in software are the ones that you've never seen before, right? But it's incredibly hard to predict what specific issues you'll encounter during the development phase, right? No one could have predicted the pandemic, right? So the better alternative is to equip engineers with the right data, tools, and most importantly, support. Which is why this last part of observability is what really distinguishes it, right? The most important part of observability and doing it well is that engineers understand how to use telemetry to figure out how and why their application is behaving the way it is. And this can be hard enough for any application, but it becomes even more difficult as our applications grow in complexity. And so complexity makes everything harder, right? It makes building applications harder, and it definitely makes debugging applications harder. And complexity makes development so much harder, right, that we as a collective industry have evolved the way that we build applications. So just like that we've evolved the way we build applications to embrace microservice architectures, we must evolve the way we debug applications to embrace this full definition of observability. So if microservices are a solution to reducing development complexity for large applications, robust observability is a solution to reducing the complexity of debugging these same applications. And so microservices and observability can both be great solutions to navigating this complexity. However, there are 3 new organizational challenges inspired by Susan Fowler's Microservice Standardization talk, which I highly recommend you watch. It's my favorite talk, that pose a risk to organizations that rush into implementing microservices and observability. And so first, we begin with the ever-common challenge of silos and drift, right? I'm sure we will hear that many times during today. And the silos and drift between different teams and organizations despite operating in the same architecture, right? And so one of the organizational benefits of microservice architectures is the new autonomy that engineers can experience, right? We love the flexibility of being able to use our favorite tools and build services in the way that we think is best, but there are serious downsides to that. First, we lose consistency that makes knowledge transferable between teams. And this lack of shared knowledge is what leads to those serious silos. And the lack of consistency is what causes drift. And so we see this happen with observability too, right? With the increasing number of tools out there, different instrumentation techniques, ways of structuring our logs or collecting metrics, we end up in a similar situation where context is specific to the service or team that you're working on. Now, the consequence of these silos is that teams end up doing a lot of duplicate work because we end up reinventing the wheel of what we consider best practices, right? And this is the core problem of decentralization. By introducing a large degree of flexibility, you lose the advantage of ensuring that teams have a minimum bar of quality for how they're approaching their work. And so next, we have a challenge that engineers are obsessed with talking about, which is the risk of having multiple points of failure. And so many of us have experienced the consequences of one service's failure becoming a point of failure for other services, whether it's within our own organization or a third-party vendor. And we understand this risk, and we have to plan for this risk, right? And this is, again, true for observability, though in a different slightly form, and that's in the form of information gaps. And so when we have a telemetry gap in our system, we risk not having the needed context for identifying all the contributing factors to an issue in another system. And this context might be essential for figuring out our next steps forward, right? And as we have more and more information gaps in our telemetry, this risk only increases. And if we're unable to determine next steps forward because of those gaps, the failures that we see in production can continue longer than they would have had those gaps not existed. So much like we need to think critically about how we plan for failure, we need to think critically about how observability gaps might lead to prolonging those failures. And so really what's at the core of these previous two challenges is that there's an inherent lack of certainty. The autonomy that comes with decentralization and distribution, right, means that coordination and collaboration efforts between teams is less necessary. But the danger with this trade-off are the assumptions that we end up making along the way about how teams are approaching observability and telemetry collection. And so when these approaches inevitably end up conflicting, and particularly when it happens frequently, right, we risk teams no longer trusting each other to provide the context you need when investigating an issue. And this isn't an exciting state to be in, right? There are both technical and cultural consequences in allowing this to fester. So how do we address these challenges while preserving the organizational benefits that come with microservices, like autonomy and clear boundaries of ownership? And so we do this by building a standardized observability platform. So the concept of platform thinking or platformization has become really popular within microservices for the same reasons we're talking about it now, right? Which is that it helps drive standardization to address the challenges that we just reviewed. And so what does this platform actually encompass in this context? Lost my train of thought. And so I define platform as having three major components: the patterns that guide us, the strategies that support us, and the stack or tools that we use. So at this highest level, right, we have the patterns that we use to make our systems observable and understandable. And in the context of a standardized observability platform, these patterns should serve this primary purpose by defining how we use standardization to address those new organizational challenges, again, while maintaining the original organizational benefits. And so the way that standardization does that in an observability platform is ultimately by standardizing the way that we communicate, both in terms of how our services communicate with one another, but also how we enable our services to communicate with us. And so going forward, I'll refer to this pattern as having standard communication protocols. Again, so let's get more specific to what these communication protocols encompass and how it addresses silos, points of failure, and uncertainty. And so there are three requirements or patterns that make up this standard communication protocol. First, we have the need for standard data specifications, and these specs should clarify the expectation of what our telemetry should look like to reduce any uncertainty that leads to those silos and drift. And getting these data specs right is foundational, right? Because this is the telemetry we'll rely on to investigate and solve issues. And when this data is inconsistent, there lacks a level of predictability and reusable knowledge that makes analyzing telemetry easier. And so essentially what ends up happening is that we spend unnecessary time building context we could have already had by building with consistency. And so to make this more concrete, let's talk about an example where logs from 3 different services in the same application have an inconsistent spec. And so pretty immediately, I can feel the cringes already. And so pretty immediately, right, we can see differences here. In the first 2 logs, right, we have 2 JSON formats, and with the same trace ID, but it wouldn't be easy to identify that as much because the key formats don't match, right? One is camel case and the other is snake case. And in the last case here, right, the camel case trace ID matches the first log, but now it's not even in the same format, right? We'd have to go through the trouble of parsing this information before even being able to match it to our other traces. And that sort of data transformation should never happen during an active investigation, right? That's friction that we can proactively solve by making correct and consistent formats a table stakes pattern for observability. And as I'm saying that, I'm holding that in mind with our previous speaker's preventative, so really love that. And so next, right, we have standard context sharing. This context sharing is governed by a set of rules for how context should be sent or propagated between services. And so this is important because the shared context is what allows us to directly connect and correlate related telemetry together. So for example, right, having a way to easily retrieve all the logs that we just saw through a trace ID. And this information that makes up the context should be, again, defined in our shared data specs. And so really what this provides us is a mechanism that services can use to comply with our standard. And so again, to ground this into reality a little bit, let's build off of our last log example. Again, so we have 2 different services, but this time we formalize the way we pass a trace ID by taking advantage of a protocol we all love and are familiar with, HTTP. And because all of our services use HTTP, we can standardize the ways that we pass context by always inserting this information into its headers, for example. And then lastly, we have well-defined interfaces. These interfaces serve 3 main use cases: collecting the telemetry data. First is collecting the telemetry data from a software component. So for example, tools that implement how we actually collect the logs we saw in the previous slide. Processing the telemetry data, and these might be separate interfaces for tasks like reformatting, deserialization, et cetera, and then exporting those to other interfaces. And then lastly, actually analyzing that data. And these are the end user-facing applications or tools that we use to investigate. So usually we think like Datadog, Honeycomb, Splunk, et cetera. And these interfaces should be well-defined, right? Because again, they clarify the expectations of how our systems are being observed. And so I do have a lot more to say on this point, but I'm going to leave it here for now because we'll actually revisit this when we talk about how these patterns manifest themselves in our observability stack later. Now, before we go into how these patterns manifest in the tools we use to observe our systems, let's revisit that full definition of observability. So earlier I said what distinguishes observability is this highlighted part, about how it's not really about your telemetry tools, right? It's about your team's collective ability to analyze that telemetry. And so far we've talked about the patterns that drive standardization. And in an easy, perfect world, right, we would set these standards and build tools to support these standards, use the tools, and become just like really awesome at debugging production problems, right? But life is much more complex than that. And so every solution introduces its own unique set of trade-offs, right? And in the case of introducing standardization to the way that we observe our platforms, our systems, we now have to start thinking about how we make sure that teams follow those standards, and more importantly, how do you make sure that teams have the skills to use those platforms effectively? And so to address these challenges, I define platform support as the second component of our platform. Because a platform without adoption, or engineers without the skills to use that platform, is an opportunity wasted to mature our organizational engineering practices. Cool, so before we head into defining the strategies guiding platform support, we have to acknowledge that building observable applications requires investment, right? Investment in time, resources, and investment in people. telemetry isn't just given to us for free, right? We have to think about observability as we're developing our application instead of just afterwards, right? Which is a pattern I've seen very common and more common than I wish. And so now, having been on many product teams before, I understand the difficulty in prioritizing this work, right? It can be really easy to devalue when you're deciding between investigating and making logging better versus some, shiny feature that your users will love. It's mostly when we're in the middle of an incident that we start to regret not having invested this time. And this tension is why many microservice organizations have come to embrace this idea of having separate platform teams. And this organizational pattern aligns well with what we've talked about so far, right? It does make the effort to standardize easier if you have a team dedicated to doing this work more full-time, instead of having to coordinate efforts across multiple teams or organizations. Platform engineering teams, however, aren't completely saved from the social challenges of this work, right? Instead of having to worry about effective coordination strategies, we now have to think about effective support and adoption strategies. And so what do these support and adoption strategies look like? The most effective strategy for enabling engineers to build observable systems is to make building those observable systems easy, right? Setting the standards we reviewed earlier is a huge step towards that goal, but we can also reuse our patterns from developing production-ready systems to further this goal. And so a common microservice pattern is to standardize the way we build services so that it's easier to build those production services, right? You see this most commonly through org-wide templates or libraries, and we can apply this pattern here too. All right, so we can take advantage of those set standards I mentioned, right, to actually implement the interfaces supporting those patterns in a way that makes them reusable and easy to integrate throughout your org. And the benefit of this as platform teams take on the implementation details that product teams would have had to take on otherwise, the more we can make sure that teams are following standards while freeing up time that can be spent tackling problems that can't be automated or implemented away. And so one of those harder problems that can't be automated or implemented away goes back to Liz's point about building up our team's ability to analyze telemetry. And this is the most important part of observability. And this is why the time that we save by consolidating efforts to build tools that support us in analyzing telemetry is so crucial. Because the biggest investment organizations need to make with respect to observability is providing engineers time to invest in their skill set. And so defining what the support for this looks like is very challenging, but the best thing I've ever done to support the teams I led in was to standardize our on-call training and what actual on-call looks like. So I know a lot of onboarding and training and it's very cringe, right? And so it's super hard to do well, right? But if you begin to see it less as just onboarding and more as like an essential feature of how you do engineering at your org, the more value you'll get out of it. And so one of the advantages of standardization is that knowledge does become easier to share widely, since we purposely build with the intention of shutting down silos. And lastly, the most effective long-term support strategy is working to embed observability into your culture. Fundamentally, this means consistently reinforcing this idea that observability is a crucial part of what it means to manage production services. And the strategies we just talked through, right, lay foundation for making observability a part of your engineering culture. But there are plenty of other ways that we can reinforce this. And so cultural change tends to happen in two ways, right? Top down and bottom up. And when executed together, these two approaches become an effective force for driving prioritization. And so for those of us who are engineering leaders, whether that's a manager or a tech lead, we can take on the work of driving this change. So for me, this has meant working with my engineering peers and cross-functional partners like product to get their buy-in that this work deserves prioritization. And so for product folks, right, just tie this back to our users, right? That's ultimately what unifies us, and that we care about our users. And so users want reliable application experiences. And so as engineering leaders, right, it's our job to translate how these technical investments translate into user and business impact. And so I'm not going to go into too many details of what that work looked like because it could be its own separate talk, but the important takeaway here is that SLOs provide a clear decision framework that makes it easier to hold your culture accountable to your reliability needs. So, sorry. Now that we've reviewed the platform and support patterns guiding our observability platform, we can start to talk about how these manifest in the way that we build actual tools that make up what we end up calling our observability stack. Cool. So what even is an observability stack, right? What purpose does it serve? And so an observability stack is basically the collection of interfaces or tools that facilitate service to service and architecture to engineer telemetry collection. And so if you remember our interface pattern from earlier, it introduced this idea that separate concerns should be handled by separate interfaces, usually through the form of APIs, SDKs, agents, etc. And so I briefly mentioned the use cases then, but just to reiterate them and put them into a larger context, let's review them again. So again, the goal here is to facilitate communication between our architecture and seen on the left here, right, and ourselves, the engineers, which are basically this like receiver part of this diagram. And so our architecture, right, uses the standard communication patterns to generate that telemetry. And our tools, those end user facing ones like Datadog and Honeycomb, receive all that telemetry so that we can have access to it as needed. And so how do we get from generating our telemetry to actually receiving it? And the answer is that we need some layer or layers of abstraction to facilitate this. And so I'll roughly refer to this as a communication layer of our observability stack. And so there are many different design decisions you can make in terms of how you separate the interfaces that make up your communication layer. But using my data engineering background here, and I split it into 3 phases that roughly correspond to an ETL ELT data pipeline. And so for anyone unfamiliar with that acronym, ETL stands for extract, transform, load, but we'll use the terms collect, process, and export instead. So again, this first interface instruments telemetry from different parts of our architecture. And once that telemetry is instrumented, we have more interfaces that process that data to standardize it. And lastly, we have the interfaces that export telemetry to our end user facing applications like Honeycomb or Datadog. Now that we've reviewed the different parts of the communication layer, we're going to shift our focus back to talking through the patterns that we should apply throughout this pipeline. So first, let's talk about 2 important design decisions with respect to our data. And the first is that our communication layer needs to be reliable. In addition to the actual data pipeline being reliable, reliability here also means that the telemetry data itself is reliable. This means that in addition to minimizing data loss and duplicate data, we want to make sure that that data is accurate and complete. And completeness should always be defined by the standards that we talked about earlier. The next design principle we have is richness, which expands how we think about telemetry to include added flexibility that allows us to collect data specific to the service and environment it's being emitted in. And so I kind of talked around this point earlier, but part of defining the specs for telemetry is also defining how a service would emit service-specific data. And the reason this is so important is because it's how we solve unknown unknowns, right? Those interesting problems I mentioned earlier. And it's not always clear what data may or may not be relevant during investigation. And so we should try to bias and reconcile collecting that information that can't be found elsewhere. And so this means, embracing high dimensional and high cardinality data. I'm aware that cost implications are important here, but embracing those instead of being scared of the complexity. And so what do these design practices look like in practice? I'll review 4 best practices that you can use to build a robust communication layer. And so the first goes back to the first pattern we started, which essentially asked, what's our shared definition of telemetry? And so I posed this question and why answering and asking this question is important, but I didn't really give an answer outside of some vague reference to the fact that traces, logs, and metrics exist. And what I'm saying right now isn't anything new, but it is important, which is that whatever shared definitions your organization converges on, they should be driven by an event-oriented model of telemetry, where an event or actually what we usually refer to as spans, is one singular unit of work. And this is because being driven by events or spans rather than being driven by traces or logs or metrics removes the limitations that we tend to put on ourselves by caring about one of these more than the other. And so in an event-oriented world, right, the best insights we get from analyzing telemetry are the insights we get from piecing together these different ways of interpreting telemetry. And so in other words, it becomes less about a singular log or metric and more about here's a thing or an event that happened, and how can I use my trace data, my logging data, and metrics to figure out what, why, and how this event even came to be. And this is flexibility that we don't always give ourselves when thinking about observability. We see these things as completely different things when they're not, right? They're just different representations of the same information. Cool, so now we have these beautiful definitions of telemetry oriented by events that we can fall back on throughout our pipeline. And remember that we care about reliability and rich data here, so what's our next step forward? And so that's instrumentation, all right? And again, we see the influence here from standardization patterns earlier. The biggest benefit of standardization is, again, the certainty that it gives us, right? And so when we talk about our data needing to be reliable, what we really mean to say is that we need to be certain of what it'll look like. We need to be able to query our telemetry with met expectations of what we get back. And so since instrumentation is what ultimately generates telemetry, it's important that the way we instrument our telemetry is consistent. That way, we have a baseline understanding of how we can expect all those events to look like. Which brings us to the next two best practices, which is that auto-instrumentation should always be your first strategy for instrumenting your applications, since it's the best way to ensure consistency. Now, I included manual instrumentation here as a fourth point because you will need manual instrumentation, right, to annotate context that's specific to your architecture or your systems or your organization. But generally speaking, that should be complementary to auto-instrumentation instead of its replacement. So that wraps up the best practices for a communication layer. What we're left with now are the tools that end up receiving all this data so that we, the engineers, can analyze it. And so when it comes to this part of our observability stack, most of us rely on external vendors for these tools, right? So like I said, Datadog, Honeycomb. And most of us aren't building our homegrown observability tools, and we really shouldn't. So instead of focusing on design practices like we did in the past section, we'll focus on criteria patterns that we can use to inform how we choose those tools. So when it comes to choosing tools, both generally, but I'll of course be focusing on observability tools, I think a lot of it really has to do with an exercise of managing complexity. We already have to learn so many tools and concepts as engineers, and we should always be skeptical and purposeful about adopting a new one. And so what does this purposefulness look like? So first and most obvious is thinking about what gap does it actually solve, right? Is it actually giving you new information about your systems? Is it actually enabling you to do something you currently can't? Right? We want to have access to the functionality that will enable us to debug, but we want to be careful about introducing redundancy, both in terms of functionality and also in terms of introducing multiple data sources to reference, right? Because the consequences are having multiple sources of data that could lead to conflicting information and having multiple ways of doing the same thing, which leads to diverging practices. And so this is the point of view you should always start with when doing any tool evaluation. Secondly, how compatible is it with our platform vision? How compatible would it be with your core architecture? Does the way we collect data work well for your architecture patterns, whether you're in service-oriented or event-driven microservice architecture? And would it require to take us more complexity by supporting new interfaces? Or can we reuse our existing tools for it? And so if we do have to introduce new interfaces, right, would these be reusable in the future? Or are these tools vendor-specific? And so next, how easy is it to use? Developer experience is always important, right? But it's especially important when it comes to the tools that you use to debug in production. Bad tools are annoying enough, period, but there's nothing more annoying than a bad tool when you're in the middle of an incident and you're stressed as hell because you can't figure out what's going on because you're too busy fighting your tools, right? And so ease of use can mean many different things, but some of the things I look out for is how easy is it to set up and adopt? Would it require a huge migration effort? How seamless would that migration experience be? And how easy is it to find and query the data that you will need? All these questions are things that you should think about before embracing a new technology. And lastly, we have developer support. I said this later, and I'll say it again. Platforms or tools without adoption, or engineers without the skills to use that platform, is an opportunity wasted to mature our organizational engineering practices. And the level of support that your organization might need can be very situational. In the past, this idea of event-driven telemetry was a new one, so I had to go through a lot of effort of shifting that culture and that way of thinking. And I think I did a decent job of evangelizing these ideas, but it's not something that we have to do alone. And so before treading into this rabbit hole alone, consider what support around the tool is available. And this doesn't just refer to the specific support provided by a vendor, though of course that's part of it, but also how is the developer community around it? And how often are they adopting standards and practices? Which transitions me to my last and final point. It's a really exciting time for the observability space, right? There are many brilliant minds thinking about this stuff, particularly in the open telemetry community, and there's still so much for us to learn and define. And so don't try to learn on your own. Learn and contribute to the communities doing this work. Because as much as the strength of your observability is about your team's ability to analyze telemetry data, the strength of your observability is also about our industry's collective ability to learn together and make progress together. Thank you.